Good morning. It's 11 o'clock on the fifth Sunday of a month, which means it's time for a special Chai and Wai session, which comes to you live from a lab at TIFR, where we try and take you up close with the science that's happening in our labs. Today, we're going to be visiting a very, very special lab where you will see the amazing world of what happens when very high power lasers interact with matter, creating a plasma and creating lots of other particles and other kinds of waves and whatever else. And to tell us about that is going to be Rakib, Ameya, and Sagar, who are all ready to tell you about it. So without much ado, let's move over and let's go to the lab and see what they have in store for us as they take us through a journey of the uphill lab. And I think they're going to explain what that is very soon. So over to you folks and enjoy the show.
So hello everyone. I'm Rakib.
So can you pin that video for everyone? I mean, can you spotlight that video for everyone, Chai and Wai?
Yeah. Okay. So what we do in our lab, if we want to say in one line, is we create very tiny stars in our lab, and then we study them. So how do we create and how do we study them and what we do? We'll show you in this session of Chai and Wai. So should we start the presentation? Yeah. So let us move on to the presentation. So I'll share the screen. And
so you're going to tell us a little bit about what happens in your lab, and then you'll show us your lab.
Okay.
All right.
Okay,
great.
we can do.
Yeah. So you show us a little presentation.
In the way we can go. I mean,
no, it's fine. Like, you can give us some of the basics, and then you show us your lab.
Yeah. Sure.
Please spotlight Rakib, the video called Rakib. Chai and Wai, please spotlight the video called Rakib, or make me co-host.
Yeah. My screen is visible, right?
Yes, but go to the slideshow mode.
Yes. I'm going to the slideshow.
Fantastic. Mode. This is good. This is good.
Yeah. So, yeah. Let's start. So in this session, we'll be talking about the brilliance of light. So how we use the brilliance of light to create little stars in our lab. And let me start with what do we study? So basically we create, So we create and study the most abundant matter in the universe. So what is the most abundant state of the matter in the universe? It's plasma. So actually 99% of our universe is actually made up of plasma. And this plasma is actually called the fourth state of matter. Now, what are these plasma actually? So suppose you have a solid. So let me have my pointer on. Okay. Yeah. So suppose you have a solid. Now, if you heat the solid up, you will get a state of matter which is called the liquid. And then if you hit the liquid further, then you will get a state of matter which is called the gas. Now, if you hit a gaseous state and increase the temperature furthermore, then what will happen? The electrons will come out of the atom, and then you will have positive ions and electrons. So you will have a mixture of electrons and ions, and that state is called the plasma. For example, suppose you have a solid, suppose you have ice, then if you heat it up, you will get water, right? Now, if you heat the water a little up, again, if you reach 100 degrees centigrade, then you will have steam of water. You will have steam, right? Now, if you heat the steam up, then you can reach up to plasma state of the water. Then what will happen? Electrons will come out, and then electron, and you will have ions and electrons, a mixture of ions and electrons, and that state is called the plasma state of the matter. Now, I'm saying 99% of the universe is actually plasma. Now, if you look around you, then you will say, no, I only see solid, liquid, and gas, right? Why is the plasma? What are you talking about? 99% of our universe is plasma. Actually, on Earth, it's so on Earth, the plasma is not very common. Sometimes we occur plasma, but it's not very common. But if we look beyond the Earth, then plasma is everywhere. So if you look, one second, let me move my. Okay. Okay. So if we look beyond our Earth, so if you look at the solar corona, it's actually plasma. Then if we look into the sun and what's inside the sun, solar core, it's a plasma. And then if we look into the nebulas that are present in the universe, that are plasmas. And in our daily life, sometimes we occur plasmas, such as when we light a fire up, so the flames are actually plasma. Then when there's lightning, the lightning is actually plasma. Also, in the northern and southern poles, we have auroras, beautiful auroras, which are also made of plasma. So plasma is everywhere outside the universe. So, and what in our lab, what we do, we create our own stars, which I have shown it here. So what I have done in here is I have plotted the density versus temperature. So x-axis is density, y-axis is temperature. Now, if you see, different plasmas are actually located at different positions, right? So if you see flames have this much density and low temperature, you can say. Now, if you see the solar core, you can say it's very highly dense and very high temperature. And if you look at our star that we create in our lab, the tiny stars that we create, it's actually very near to the solar core. So that's why we call it a star. But particularly speaking, it's not a perfectly a star, because you have to have stellar equation to be a star, right? So it's not a actual star, but we create conditions very near to the solar core. So that's why we call it our own star. So if you look around the universe, it's plasma everywhere. So if you look around the star, you can have solar flares, which are plasmas ejecting plasmas. Then in the interstellar medium, you have plasmas. In the Earth core, you can have this plasmas, and also in lightning, you have plasma. Now, how do we create these stars, tiny stars in our lab? So what do? We deliver very high power to the matter. Now, the next question is, how do we generate such power that we give? Okay.
So by power, what do you mean by huge power?
Okay. I'll explain it maybe in next slide. So what do you mean by very huge power? So we do it with very high laser, very high power laser. Now, how do these lasers produce very high power? Okay. So, the power is actually energy over time. So you can make the energy of the laser very high, or you can make the pulse time of the laser very, very, very short, or you can do both, right? But it's not actually that simple. So what do? We create a light pulse which is very, very short in time. We call it a femtosecond pulse, or an ultra short pulse. Now let's understand what is a femtosecond. Suppose you have 1 second. Now if you divide it by 1,000 times, you can have millisecond. Now what does a millisecond look like? So a millisecond is like a camera flash timing, typically. Now if you divide 1 millisecond in a million parts, then you can have nanoseconds where the computers actually operate in that region. Now if you take that one slice of a million times and then divide that in more 1 million times, then what you get is actually a femtosecond. So if you compare this 1 femtosecond with 1 second, it's 10 power. If we convert it in 10 power, so it's actually minus 10 power minus 15 seconds. So if we want to compare it with actual minute, so 10 femtosecond to 1 minute is actually 1 minute is to the age of the universe. So it's tiny small amount of time. So for that particular time, so our pulse, so what we send a very small laser pulse, but it has a huge energy. So with a huge energy, with a very short pulse, we send that laser pulse and we interact with matter. Now what we get, so our pulse generally have 3.75 joules of energy, and it's around 25 femtoseconds. So what we get is we get 150 terawatt. Terawatt is 10 power 12. So we get 150 terawatt of laser power or peak power delivering to the matter. And if we focus it to a very tiny amount, tiny amount in space, that is 10 micron spot, then we get something like 10 power 19 watt per centimeter square. Now, if we want to compare this with the sunlight, if we take the whole power output from the sun, and then we focus it to 1 point of 0.1 mm square, which is typically a dot you can make with a pen. If we take the whole sun energy, not the energy that is coming to the earth, the whole sun energy, and focus it to that point for that particular femtosecond, then what we get is what we are delivering to the matter. So we are delivering very, very high power, actually high intensity to the matter. And that's what creates the extreme state. So in this slide, you can see if you have a gaseous cloud, and then our pulse is coming, then it ionizes the matter, and then electrons go out, and you have a bomb blast kind of thing. And then what you get is you have energetic ions, energetic electrons, energetic neutral particles, energetic negative ions. You get all sorts of particles. Now, in a nutshell, if I want to say, so if we have a target like this, so something as a target we use, we'll show you later. So then we focus our laser at a 10 micron spot, which is very tiny spot. Then what we get all sorts of radiation from it. And then we get high energetic electrons, high energetic protons, and other atoms. Now, how do we create this kind of stars in the lab? Is with the help of the laser. So in our lab, we have two lasers. One is 20 terawatt laser, which we'll demonstrate in a bit of time. And then we have a big laser, which is 150 terawatt laser system, which is one of the biggest laser in India. And so I'll give the platform to Sagar, and Sagar will explain how this laser works and how do we create this very small pulse in time, and then we'll move on. Yeah. So thank you. Over to Sagar.
Yeah, thanks, Rakib. Hello, guys. So, yeah, so I think you have seen most of you have seen the lasers. Mostly we use the pane lasers to point something, or the lasers we get in the fair to play around. Now, how does a laser work? So basically, to make a laser, we need some system which has multiple levels, and we need the thing that the electrons in that particular system try to stay in the upper level, so that when it de-excites from the upper level to the lower one, it accumulates an energy more and more. Now there is a common thing, that when you drop a ball from the higher level, it will always go to the lower level. So how do you keep it in the upper level for a long time? That is why you need to keep it pumped. It is called a pump. So let's say here I have shown this one. This one is the diagram of a laser, and these are the atomic level. So when you excite the energy, it will go in the upper level. It will come to the metastable state, which is called this is the technical term you don't understand probably, but this is a state which has a very short lifetime. Then some same energy photon comes here, takes the electron from the upper level to the lower level. It emits another photon, so the energy gets amplified, and then it comes to the ground level again. And this process we repeat again and again by putting two reflectors, one in the left side of the laser and one in the right side of the laser. So the beam just passes through again and again in this way, round trip, and it amplifies it. Okay, so these kind of lasers are continuous, that this pane lasers and other things. In our lab, as Rakib told, that we use very short pulse laser, we need a very short time scale of the laser. So how do we create that? We have two kinds of laser. One is called nanosecond laser, which works in nanosecond time scale. Another is femtosecond. The nanosecond lasers generally work in a principle which is called a Q switching. This is some technical term. I'm not going into the details, but this is some technique that we use to generate the pulse. And for the femtosecond laser, we use the mode locking technique that you will see. So in the mode locking laser, what is happening is that you know that in any light has some different properties like wavelength, frequency. So if you see the frequency of some continuous laser, it is very narrow. It has some particular frequency. The red laser has some particular frequency, 780 nanometers, like that. Now, if you see if you increase the bandwidth of the laser, which is the spectral broadening, I mean, the width of the total spectrum, then as the spectrum increases, the pulse duration decreases. That is how we increase the spectrum, superpose all of them, and we make. So here you can see the zip file that red, blue, and other colors are superimposing. And here in the downside, you are creating a pulse. And in this way, you can create some femtosecond. So these femtosecond lasers are very high power. How do you amplify them? Because this high power can damage the optics and other things. So you first stretch them from femtosecond to picosecond region so that the power decreases. Then you amplify them with different amplifier stages. Then you again compress them so that this peak increases.
How many pulses per second can you create?
So right now we can create some 10 pulses per second. It works in 10 hertz. So it comes like tuck, 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 10 hertz, and then it amplifies, then it goes. So when it goes away, it takes a huge power, and then we use it in the chamber.
And is there any limit? Like, can one have more than 10 pulses?
Yeah, obviously. So there are kilohertz, megahertz lasers that we can use, but for that, the overall power should be decreased because otherwise it should increase the thermal. So the pump should excite the atoms sufficiently enough to get sufficient number of pulses. So that is it. Okay. So this is just to tell you that how do we stretch the pulse and how do we compress the pulse. So when the pulse comes, let's say this is a particular type of stretcher. We have a prism. And you know, as there are different lights, one is red, one is blue. Red will follow this path in the prism. Blue will follow this path in the prism. So you can see clearly that the path length of red is smaller than the path length of blue. So when it is coming, red and blue are coming together, and then red is going forward, blue is coming backward. So overall, that is getting stretched. In the compressor, we do just the reverse process. You can see here, we are doing this. So red is following bigger path here, red is going to the longer path, and blue is following the shorter path so that it gets compressed. Okay, so now we are going back to our laser system, and we need to show you something, guys, in the actual form. So let's try it now.
Yeah. Yeah, you'll have to stop the show.
Yeah, so this is a torch. This is not a laser. This is the laser. The basic difference is, as I told you, the population inversion and creating the state so that it can hold the more number of electrons in the higher state for all the time. Now, this laser you all know, this is a very low power laser. If I shine, you can see this light. This is actually a green laser. Anyway, it's a green paper also, so I don't think you can understand clearly. Now you can.
Maybe you can turn off the light momentarily.
Yeah, just turn off the light for a second.
This one.
Okay.
Ah, now we see it.
Yeah, so you guys can see the green laser. Okay. Yeah, so now we are going back to our big laser system, the big box. So this is our laser system that we use. This is the oscillator. So this creates the femtosecond laser pulse. Inside this oscillator, there are multiple. So this is found by another green laser, I think you can see the green flash sometimes. That is not the laser that we are using. That is just to make the population inversion. That works like a pump. And here, it creates an infrared laser that is not so much visible, close to 800 nanometer. It comes after the mode lock. It is a femtosecond laser, goes here. This is the part of the stretcher. And inside this big box, I just show them the big box. This is the big box. So here is the stretcher. Here we have an amplifier. Here we have the big amplifier. And finally, after all these amplifiers, yeah.
So can we open the box?
Yeah, sure. So,
Okay. Okay, guys.
okay. So
The laser comes. The laser that we make that comes from here. Then it goes inside. Then what Sagar explained is we have a stretcher which actually stretches the part, right? We created the short pulse. Then we stretch it so that it doesn't damage our optics. So for that we have the stretcher. I'm not going to show the screen here. Here you can see there's a big mirror and there is a grating, and we use this mirrors and grating to actually stretch the pulse. After that, we amplify it from that side. Sagar can go that side and show me.
sure.
We will open up, and as you can see, we are using goggles because we don't want to damage our eyes. So we are always.
So you can see a red spot there. I can pinpoint, but my hand is there.
You can see one green line that is coming. That is called. We call them the pump laser. No, different. Okay. And then what you can in the center you can see something which is blinking, which is actually red.
So this is basically the active medium that I just showed. Inside this, the population inversion is happening. Green is the pump laser that is taking the electron down from the upper state to the lower state and is amplifying the laser. So this is how the amplifier. This is a smaller amplifier. I cannot open the big amplifier right now because it has a huge amount of green inside this. Anyway, so after this, the laser gets emitted from this. This is the end of the laser. I mean the amplifier part. This is not the end. This is the amplifier part end. After this, it is going, and this is the laser beam. This is the amplified laser beam. So after this amplification, Amir, lights on again. This is our compressor chamber. This big chamber. Inside that, we have another grating, pair of grating, and we compress the beam to the experimental chamber. So now, Amir,
taking the light, taking it, again compressing it.
We are taking the light, stretching it, amplifying it, making it more energetic, compressing it, getting it proper shape,
then we
transferring to the.
Now you're getting your power shot.
Yeah. And I think you can heard a tuck 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 sound. This is that 10 hertz sound as Ulas was asking how much. Yeah. So now it's over to Ameya. Ameya will tell about what we do with the laser.
So we stop the video from here and then we screen share.
Hello. So hi everyone. So I will tell you about what happens after the laser and how it is focused to become a plasma. So let me just motivate you, as Rakib told that we just create a star on a tabletop. So I will just let you know the difference between the sun, our sun, and the star that we create. So as we know that the sun is just a ball of a hot dense plasma, but our star is also a ball of hot dense plasma that we create over here. The temperature at the center of the sun that we create is about 15 million degrees Celsius. The temperature we create right here is also of the same order. The radius of the sun is very large. It's around 700,000 kilometers. But but we can create a similar temperature in a very small radius star, which is a 10 micron star, which is just the 1/100th of the thickness of the hair. Uh, the life of the sun, as we know, it's a very long-lived. It's around 100 billion years. But 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 the plasma we create is of the order of the 1 nanosecond. Uh, so, uh, so as we know, the sun shoots very high energy particles, so solar flares, and it has very high magnetic fields of the order of 4 kilogauss to 10 kilogauss. So we also create in such a small space, in such a small time, we create the magnetic fields around 10 to 100 kilogauss. Just to give the comparison, the fridge magnet that we have is of the order of the 5 gauss. So we can understand that the 10 to 100 kilogauss is a very huge magnetic field. And also it creates very high energetic particles such as X-rays, UV rays, and electrons, protons, and many other particles. The sun, to study the sun, is very far away from us. It's around 150 million kilometers. But the star that we create is just a few meters away from us. We can study it anytime. We can create it anytime. And it's easy to access it. So it's a much better way to study the plasma physics or to study the properties of the sun. And we will show in a few times that our star also glows. Yeah. So following to the next slide. So we have this laser plasma interaction that we talked about. So when a laser hits in a very small area, it creates electrons, it creates protons, it creates X-rays, it creates UV rays. So we have different diagnostics to study these electrons, to study these X-rays. So behind me there is an X-ray detector, so which detects the high energy X-rays. So we also have a high particle detector, which is electron detector. So I can show you in the camera. So what happens? We have a stream of particles coming from this small hole, and the small hole we have this magnets which bend the particles onto the detector. The detector is sitting inside, so we can just measure the energy of the electrons, and just we can understand how much energetic electrons is been created. We also have techniques to measure the magnetic fields. So one popular technique that we use is the Doppler shift measurement. So we know that once the plasma is created, it will expand very rapidly. So it will expand very rapidly. And to give an analogy, I will just tell you about, you must have heard the sound of an ambulance or a police van. So it creates a very vibrating sound, as we see. So why does it create? Because the moving source, when it travels with a certain speed, it just changes the frequency of the sound. So by this simple phenomena, we can just understand how fast the plasma is expanding. So let's say we have a density of the plasma, very high density of the plasma, and it expands. So we can understand by the Doppler shift, if the source is moving towards us, it will be blue shifted, or if the source is moving away from us, it will be red shifted. So by this simple technique, we can measure how fast the plasma of our star is been expanded, and the results we get, the speed is of the order of 1,000 kilometers per second. It is much faster than the spacecraft we have at this current time, which is very low. So the next I will talk to you about the second harmonic generation. So what happens? Let's say we have a plasma created, and we have the laser, which is of the 800 nanometer, which is in the slightly infrared region, and it vibrates the molecule and it emits at the same wavelength. But let's say we have a lot of energy like we have over here. So when very high intensity comes on the molecule, so it vibrates to a higher excited state, and before it comes down, it again excites it, which will make it emit a blue light. So basically, we just created an 800 nanometer to a 400 nanometer, which is just a red light to a blue light. So we will demonstrate in a short while how does it emit, and how does we create a red light from the blue light. So we'll explain it over here. Yeah. Yeah. Light. Laser. D6 laser. Okay, we are ready, right? Video. Host has disabled it. Video. Okay. Okay. So you can see this red light over here.
Let's go a bit close.
So we can see the red light over here. Yeah. So now I will show you how it is converted to the blue light as I explained. So we will introduce a material which will change this property. So as I said, the molecule has to vibrate and emit the blue light. So we are introducing the material, and the material has to be at an exact angle to make it work.
So now it's blue.
So now the rest of the laser, so as I can show, before you can see it is red, but after you can see it is blue. So that's the magic of the nonlinear optics. So it is just the simple molecules vibrating very rapidly and just emitting the blue light.
Now you will say, so why don't we get this in normal light, right? You can ask this, why don't we get this in normal light? So what is so special about this light? So the thing is, this nonlinearity actually comes because of the intensity. So in normal light, whatever we use in day-to-day life, that doesn't give you much intensity that this laser gave you. And the material's property actually depend on the intensity that you put on the material. So as you put very high intensity, the refractive index of the material actually changes because of this intensity, and that's why you are getting this nonlinear properties of the material, and that's what is giving the interesting features of this material.
So there is this question: is there any possibility that this tool can perhaps be used in future to see something that is unseen so far, like dark matter, online? Is it
okay? Not really. You can't see matter with it because it has only to do with light. So it has only to do with light. So whatever fundamental light it is coming,
is actually not real matter that we use. Light interacts with this real matter, and for dark matter you need to.
Yeah. So also for this to happen, we need to understand all the properties of the matter it is passing through. And since we have no information about the matter that we need to find, it's very hard to observe this phenomena in case of dark matter. But maybe some other technique might help. Sure.
And also, there are some conditions for which, so suppose you put a normal glass plate and you want to see this conversion from red to green or red to blue. So in normal glass, you won't be able to see. So there are some specific crystals that give you these properties. And
so to demonstrate that, I will just change the angle of the crystal at which it is incident in, you can say, the instant change. So the intensity of the blue just reduced with a very small tilt of almost a degree, 1 degree or something. But yeah. So now we have light and we have no light. We have light, we have no light. So it's very sensitive to the angle at which it is been incident. Yeah. So the crystal is very important.
Blue is what we are seeing is actually the reflected light from the material.
Not reflected,
transmitted.
Okay. It's passing through the material, and when passing through, it is getting converted to its second harmonic.
Yeah. But this light which we are showing is not yet focused yet. So let's say what will happen if we have the more light focus on in the air. So what will happen if we focus it very high intensity? So we have some more non-linearities coming into action, and we will show it in a while.
Okay, so what we are going to show now is our whole laser beam is coming, and then we want to focus it to a particular point that we discussed. We will focus it at very tiny small point, and then we see what is happening. So right now we are reducing the laser energy, and then we'll focus it. So we have reduced the energy, right?
Yeah.
So
Yeah.
actually,
Yeah, just ensure that the energy is reduced.
Yes. Yeah, now the energy is reduced and the beam will come to that hole behind that. We'll call on that mirror. This is the focus. Okay, so for focus, generally we use some lens or something. For special type of focusing, we use called a parabolic mirror. You can also focus it by a lens, but we use. Anyway, so I'm opening this and turn on the light. Okay, so you can see this. This is the.
So there's a spark.
That small point is the star which I am talking about. This is focused when all the energy, very high intensity energy, is focused on a very small area in a very short amount of time. So what happens? It is the spark, the sound is coming because it is stripping the electrons from the air. So air is of the nitrogen, oxygen, and all the other elements. So it is that high intensity localizedly. It is stripping off the electrons from the air, the molecules of the air, and which is what causing the light and the spark. So now we increase the energy, laser, and we show how the spark is. This is just the low energy, so we will just increase the energy and show you what happens. Ready?
How much energy was that in kilowatts or megawatts or something?
That was around 1 to 2 watts, and this is now 20 terawatt full energy slot. So this is low energy, and this will go to high. Okay. Again, go to full energy. So now the spark has been increased, and just we can see that it is throwing a lot of light. Right now, it is also ejecting a lot of electrons. So we generally do all these experiments inside the vacuum, but just to demonstrate what is happening, we are just showing it in the air. Yeah. So you can see on the other side, there is a lot of light which is generated. So let's take a pause and just observe this light for a while and just try to understand what is happening. Okay, so just enjoy the light for a night and then putting a filter to just put a filter. We are putting a filter, and after that you will be able to see the light properly. Yeah.
Just hold the camera a bit steadier.
Okay.
Moving a bit.
One second. Keep the camera. Just give us a second.
Yeah, this is good.
Yeah. Now let's put a filter. Okay, we have put a filter. Now we can see clearly, right? So you can see different colors that are coming. So, but we have shown you that our light that we are sending, that is actually a red light, right? It is 800 nanometer. It has some bandwidth, so it is actually looking like a red light. But what you are seeing right now is as we have focused it to a point. Now after that you are seeing different colors are coming, and this is beautiful. This is looking very beautiful, right? Now, why is this coming? So, Amya, can you explain this? Why is this coming?
Okay. Okay. So what happens when we focus it very tightly? So we have higher order non-linearities of the air which is present, which will start to introduce, and the properties of the material will change, which is dependent on the intensity that we are hitting. So the properties of the material, such as refractive index, will change as we focus with an higher intensity, which will create a huge bandwidth, or we can say which will create a lot of color, and these colors is what we are seeing. So if we reduce the intensity, the properties of the matter will reduce, and then we'll show you. Let's go back to low energy mode, and you can see very single color, or yeah. So in the low energy mode, if you can see that we are seeing only red color, but to see more and more colors, we need to put higher and higher energy. So again to our energy mode, and And yes, so now we can see green, you can see yellow, you can see blue. So we can see all shades of color. So this is the magic of the non-linearity. So earlier, the second harmonic generation, which I showed you, that was the crystal, which is a specially designed crystal, which is dependent upon the angle and the orientation. But this is a non-linear property of the air. The simple air can also induce non-linear properties if we have enough energy or power or enough intensity into it.
Yeah. Okay. So there are two things you are saying, right? One is different colors are coming, and one is there's a sound, tuck 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 sound that is coming. So Amya explained how this different colors are coming. Now Amya, just tell us how this sound is coming.
Yeah. Okay. Okay. So what is happening that when so what happens? So now as I'm talking, how do we hear the sound? If a person is standing in front of me, so it happens due to the pressure waves, right? The sound waves are the pressure waves which creates the vibration in the air and just travel to the opposite person. So this sound, so when very high energy pulse hits the air, it will ionize the air and it will create a shock wave. And that shock wave, when propagates with a very fast velocity, it's like creating a sonic boom in a very small area. So this sonic boom is what we are listening, like the sound right now. So if at very high energy, when the pressure is compressed very fast, very rapidly, so in this way the shocks are created, which is what we are hearing right now.
So is there any way I can, if a screen, when we see it, see a distribution of color?
Yes.
So is there any way I can switch red from right to left and the blue from left to right?
No. Yes. Actually, it depends on how your focal spot is. If your focal spot is perfectly symmetric,
okay,
then you should get a light every color everywhere.
Okay.
So you should get like rings of color, because of the dispersion, every color will disperse a bit. So you will get rings of color. You should get rings of color.
Okay.
But if you have slightly deformed focus, then you can have distributions different.
So you,
because at particular points the intensity is becoming different, right?
okay.
So that's why it is very much dependent on intensity and how the intensity is changing with time, and also in the space how the intensity is distributed. So it depends on that.
So it's not random.
It's not random.
Yes. It's not random.
It's not random.
Yes.
Yes.
Yeah. Yeah. But let's say if you want to create a light which is only green from the red, so we need to create a crystal in such a way that it has properties which is specific to that wavelength.
So it's basically the medium on which
yes,
you are shining
yes.
the light.
So everything is dependent upon the medium and the properties of the medium, and how light is kind of manipulating the properties of that medium.
Okay. So what we are seeing right now, we are focusing the laser on the air. But when we do the real experiment, we don't do it. So what do? We focus the laser on a solid target. And the solid target, we can see for a time being, we can stop the laser and light. Lights on. Lights on. So for a time being,
Let's go to the.
Yes. So for the experiment basis, to study the high energy electrons, X-rays and UV rays, so we just shoot the light on a target which just looks like this. This is the target which we shoot on, and as you can see,
Hold it in
your right.
Hold it in your
yeah.
right. Hold it in your right.
Yeah. No, it's okay. 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 So you can see small dots on it, right? So these dots are the exact shot location. So each dot is a separate plasma. So we move this target in the vacuum and we take a shot. We study its electrons, the magnetic fields, the X-rays, the light coming from it, and we just move the target, then take another shot. We just create a database and we analyze it, and we get to know what kind of plasma is formed. So these bigger dots are the high energy dots and the smaller dots are the small energy. Because the plasma, the temperature, the magnetic fields are small in a smaller dot, and the bigger dots, the energy, electrons, magnetic fields are very huge. Yeah.
Now, what we have demonstrated with the energy, that energy is, so we have this 20 terawatt laser. But right now we are only using like 20-30% of the energy of the laser. So we are not using the full energy because we are in air. Because when we do actual experiments, we need to go vacuum, because when these lasers actually propagate through the air, it starts to ionize the laser, ionize the air, and then, yeah, so it starts to ionize the air when it's propagating, and then we lose the energy of the laser. So what we do, we cover the things up, we make a vacuum chamber, and then we send this high energy laser to our chamber, and then we focus it to a point, and then at the focal point, we put this target. Now we put this target, the laser focuses on it, and then we give a laser shot. So right now what you are seeing, you are hearing tuck, 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 tuck. So we are sending the laser continuously. So 10 laser shot is coming at 1 second. Now when we do actual experiment, what we do, we place the laser, we place the target there, and we have automated everything. So what we have, the laser comes, hits at particular point, then it damages that. So what we need to do, we need to shift the target a bit. We have stages for that. We shift the target a bit, then we take the next shot, then we shift the target, then we take the next shot, and then these plasmas are being created at that particular point, right? And then we want to study how these plasmas actually evolve, right? And then how these plasmas evolve, how do we study? We have different mechanisms and we have different setups for that. So sometimes what we do is we call it as pump probe technique. What we do, we create the laser, we create this this tiny sun or tiny stars with a particular laser. Then we take a small leak of the laser and then we study it with that. Okay, so because that thing happens in very, very, very fast time. So with the femtosecond, we are creating this, and within 1 nanosecond or 2 nanoseconds, the thing is gone. So it will have.
You are saying that the plasma is very short-lived.
Very short-lived, yes. And in that particular time, we need to study it. After that, there is nothing. After that, you give another shot and you get for some nanoseconds, and then that is blasted up. So you need to study your thing at that particular nanosecond time. So for that, we use different techniques, and we can maybe show them.
The idea is, again, just to recap, you use this high intensity laser pulses to create a plasma.
Yes.
And this plasma is very short-lived.
Yes.
And you have tools to probe what happens in that short time.
Yes.
To the plasma, and then that's basically the physics system.
Yes. So what is happening when we focus it on that? So it's like a tiny bomb that is blasted at that point. Now the plasma created, so everywhere else is vacuum, because we have kept this target in the vacuum chamber, right? Now everywhere else is vacuum. Vacuum means you have sucked out the air from inside, right? Now when you hit this target with the laser, the plasma is created, and then the plasma is coming out, it's getting blasted like this, it's exploding. Now we need to take the snapshot of this. That's why we use some techniques called pump probe, and with that we study how the plasma is evolving with time, how in femtoseconds or picoseconds the plasma is evolving, and then we have simulations, we study them like that. So maybe we can show them the actual.
So basically, between one pulse to another, are you always sure that the entire plasma is kind of consumed and you're?
Yeah, that assumption you need to take. Otherwise, you won't be able to do this thing. So every time when we do, we assume that the plasma that we create is like homogeneous. Like every time it's like reproducible. That's the assumption that we make. But that may not be true every time. So depending on, suppose that your target has some.
This is one of the parameters you verify as a part of your study, that there is uniformity.
Yes, because when we make this target, we take care of this thing. We see the target is very, very flat. Otherwise, what will happen? We won't be able to reproduce the same plasma kind of thing, same condition.
So what all things can qualify as a target for?
Okay, so for different experiments, we use different targets. So sometimes we would, if you look into the target, so it has a small coating of aluminium on the top. Then we have in the back side that is actually glass. You see from the side.
Yeah.
So it's actually a glass, but over that we have something like 200 nanometer aluminum coating. And that coating we use for experimental purposes. Sometimes we use normal glass targets, sometimes we use foil targets, because this, or sometimes we use grating targets or structured targets that are specially structured on the surface, because depending on your surface, the laser plasma interaction sometimes changes. And then you can have different particles at different directions, and that we wanted to control sometimes, and then what we want to enhance sometimes. And for these things, we use different tasks.
So on target, so we have some targets we will show right now. We have some foils. So foils are very thin, so we can enhance some phenomena in foils. So on grating, let's say the gratings have very good quality of resonance. So we have certain resonances or certain phenomena which are been only specific for the grating. And if we incident at a specific angle, the laser, the plasma is created, the electrons, the hot electrons and the high temperatures are created in a very certain direction. And we can study only one direction. We don't need to have a very uniform direction. So we can just create electron beams which are at a certain direction. And these electron beams can be used in medical purposes and for cancer therapies and such like that. So we can create very high energetic monoenergetic electron beams. So similarly, we can also create high energetic uniform X-ray beams, UV beams, or maybe something like a proton beam and like that. So the type of the target will tell you about what kind of phenomena is well looking of. So now we can show you the main chamber and the laser room, the second laser that we have, which is much more high energetic. And the laser right now, the colors that we shot were the ones were almost 10 times less than what we have over here. So we have much higher power laser. So we'll show you over there. Yeah.
Okay, guys. So this is our experimental chamber. I mean, for the big laser, this is our experimental chamber.
Maybe you can just show it from a bit longer distance so that people can see the full chamber.
Yeah. So the laser is down to the other room. That you can see the pipe, the steel pipe. It's coming
from this. Yeah. It goes from inside this line, and then we have mirrors.
We have this mirror. It's a specially designed dielectric mirror.
These are big mirrors.
And then it is going to the experimental chamber. So at the experimental chamber,
inside the chamber, we have a lot of diagnostic setup. So let's say the beam comes from here. The beam comes on this mirror and it travels a path and it is focused at a point. So this was a target which I showed you earlier. So I can just mount it over here simply. And then it just focused at a point over here, and after the electrons and the magnetic fields are produced, we have different optics and different mirrors to analyze what is happening inside that plasma. So we have different optics. So this is a pump probe technique right now, which is aligned right now. And also we have a camera which will image the plasma. We can image how small it is focusing on to maybe sure to get absolutely sure about what the intensity we are hitting on. So outside during the analysis, the beam comes in the outside region, and we can see we have different diagnostics aligned over here. So we have cameras which will see the plasma, which will record the light of the plasma, and we can have the spectrometers which will analyze the spectrum, the Doppler shift, which I told you earlier, the how fast the plasma expands. We have various diagnostics aligned for it.
Yeah. Now let's go to the other room, which is our main laser room.
To show you from where the laser is coming. So the laser we showed you was 20 terawatts, but right now
So yeah, this is our laser room. So this is our laser room, and and the big laser. So the whole room. Yeah. So this room is actually dedicated to the 150 terawatt laser, and the laser starts from here. Then we have the oscillator here. Then, as Sagar explained, we have different amplifiers. So as you see these boxes, this box, every. So let's come this way. Yeah. So as you see these big boxes, these are actually amplifiers that amplifies or that enhances the energy that is contained in your laser. And then what do? We have this big amplifiers, and then after that we move on to the compressor chamber. So you see this beam, this is a very big laser. Yeah. After that, the beam comes from here. It comes out from here. Then it enters this, which is called the compressor chamber. And inside the compressor chambers, we have the gratings. So first we stretch the pulse, then we amplify it. We increase the energy of the laser. Then in here we compress the laser back. So we make it again femtoseconds, and then from here the beam comes out, and this beam is going and it's going to the other room. So that side is the room that we showed you earlier. So that beam goes and that beam bends. We use the beam bender, and then we send it to the experimental chamber. So everything that you see starting from here stays in fully vacuum, because this is a very high power laser. So when it propagates, we don't want to interact it with the air. So that's why we put it in vacuum. Yeah. Yeah. Now let's go again to the experimental room, and for the last time we can show them the super continuum, and then we sign off. Yeah. Okay. So for one last time, we'll show you the magic of the light.
No, I want to see it again and again.
Yeah.
Why last time? Why is it that they're having double doors and things like that to enter the lab? Compared, is it expected to be some?
Yeah.
Thing is, so that the laser stability depends on the humidity and the temperature.
Okay.
So we need to maintain the humidity and the temperature inside the laser.
Okay.
And also the laser needs to be clean, right? So the laser room needs to be clean. So we have different air purifiers, we have dehumidifiers, we have air cleaners, we have everything set up in that room, so that the optics in that room doesn't get coated with dust and all.
Particles and debris.
We wanted to keep the room.
So controlling the ambient conditions is important for the stability.
And also we have multiple ACs in the room, so that we control the temperature. So always we keep the temperature around 20 degrees centigrade. Otherwise, your things will get heat up, and then your laser can behave differently.
Okay.
So yeah, that is a very important.
So the environmental conditions are pretty
Yes. So now,
very important to have.
Yeah.
No, double.
Yeah.
Air conditioning is fine. Then double is for another reason. The cavity you see outside, you have to stand there while the experiment is going on. You can't stay inside because of the radiation. Okay. So it's for the safety as well.
This room. For this room, we use this because when this laser interacts with the matter, it gives you different radiations. So all sorts of radiations will be there, right?
Correct.
So to also get to protect ourselves from the laser, we move out of the room and we control everything with the computer.
Correct.
We don't enter the room when the experiment is happening. So we control everything from outside, and then we take the shot inside. So we have cameras installed, we can see everything.
So it's important for experimenters and also for everybody to realize that these light matter interactions at such a short scale, at such a short time scale, and when such huge powers are involved, can generate things which you perhaps may not like for your own health.
Yes,
That is
that's right.
For example, to say when we have a very full energy shot, so even the linear stages and the electronics fail after one shot because there is a huge electromagnetic pulse which
That
goes
comes-
on, which will damage the electronics. So we need to restart all the electronics back again.
Okay.
To get
Yeah.
it. Yeah.
So yeah, so now let's increase the laser energy and let's show you the magic. I'll turn off the light. Is visible now? Okay, we need to put a filter on the camera because otherwise, yeah. Okay. Okay. So this is what we call the super continuum generation. And
So
yeah,
you have any video when the beam is very properly focused?
actually, these beams are coming from,
a lot of effort to.
It's a lot of effort to focus it like this.
Okay.
Because this beam actually passes through different optics and transmitting, because these crystals from where these beams are generating, these are very big crystals. So you have some deformities in the beam. So
Okay.
when you don't have a very smooth beam, which you call the Gaussian beam, that you can focus it very well. But when you have these deformities in your beam, you can't really focus it to a very small amount. So we can go up to like 10 micron, but the actual limit that one can get with a very smooth beam is something like 2 micron. But we are getting something like 10 micron because it's passing through a lot of optics and it's actually getting, the beam is getting distorted a bit.
Correct. So basically, the environment is kind of distorting the beam.
Yes. So yeah, so that's all from us. That's all from Afil.
So
And
let's turn on the light.
Yeah.
And maybe you can.
Yeah, let's turn off the laser.
And then we can take questions.
We are happy to answer questions if there are any. Yeah.
So guys, fantastic. So now let's take some questions. So the question is, can nuclear processes be triggered in the atoms with the glowing dot?
Yes, you can. Actually, so people are trying to, not with this glowing dot, but you have to put like very high energy to get this thing. So it's not actually possible in here right now, but in the world there are systems, or there are systems that are giving that are moving towards the fusion energy. So with this big lasers, with the help of this big lasers, you can actually create fusion. So what is happening inside the sun to produce energy? So how does sun produce its energy, right? So it's doing a fusion inside it. So the question is, can you do fusion with this big laser system? So the answer to this is, people are trying, but they have not achieved actual fusion. But we are in a process to do it. So there are systems like National Ignition Facility and there are techniques called inertial confinement fusion and magnetic confinement fusion, which are trying to make fusion in the fusion energy. Yeah.
You mentioned that the experiments are done under vacuum.
Yes.
So what is the level of vacuum you require?
Okay.
And initially the question is, can this not be done in ambient air at all?
No, not at all. Because when this lasers propagate, so what we are showing you here is we reduce the laser energy a bit, a lot, because otherwise we won't be able to do this here. So when we do actual experiments, these lasers have very high power in the beam. So when this beam propagates, it will start to ionize the air, which through it's propagating. So it starts to lose energy. So you can't do these experiments without vacuum. Yeah, you need to go to vacuum to do this experiment. Yeah. And the vacuum level is
about -5,
-5, -6.
It's not ultra high. It's not ultra high vacuum, but it's not like -1.
And you mentioned that you have several cameras to detect the signal.
Yes.
So what exactly, can you elaborate a bit on the
Okay.
detection system?
Okay. Sometimes we want to image how we are focusing. So we reduce the laser energy a lot, then we focus it to a point, and then at the focal point, we have some objective and a camera setup. Then we move the camera there and we see the spot, how it's looking, right? Then we measure how the focal spot is, how big is the focal spot, that we measure. Then we have other cameras, like we have very sensitive CCD cameras, which actually we wanted to measure magnetic field and all. So we set up a pump probe setup and then we image the probe there. So these cameras are really high-end cameras, so CCD cameras we use. Yeah.
And during the course of description, you mentioned that some particles come out as a result of light matter interaction. So what particles are these, and how do you study these particles?
So these particles are basically electrons, protons, ions. These are the main particles. So we study the electrons by using an electron spectrometer, like I showed you over here. This is a basic device. This is an electron spectrometer. So basically, electrons come from this tip.
You can show them the hole, I think. Yeah, this hole.
So we have a small hole, and then inside we have two magnets. So these magnets will bend the electrons because the electrons have a charge. So they will have a force which is V cross B, the velocity versus the magnetic field. So they will have the force downward, and we can just put the detector inside, and we have the trace of that trace of the electrons inside the detector, and we can study how much energy we have. The higher the energy, farther it will go, and lower the energy, nearer it will go. So we can understand where the dot is. We can understand what energy the electron has.
So you can estimate the electron energy from the location.
Yes, yes, from the location. Yeah.
And there's another question. So there is a national ignition facility.
Yes, we
mentioned. Are the lasers similar to?
Not really. Okay. So in the national ignition facility, they use this. So our laser is a femtosecond laser. So our laser, the pulse time that we talk about is 25 femtoseconds. But in the national ignition facility, they use nanosecond lasers. They have 192 beams. So 192 beams come at a particular point, and they have kilojoules of energy. They have tremendous amount of energy, and then they focus it to a 1 micron point, 2 micron point, right? And then they put a very tiny target there, and they wanted to implode everything. So you have this tiny target, and you put lasers from every side. So as you know, these lasers have pressure, right? Because of the radiation pressure. It's called the light pressure or the radiation pressure. And due to this pressure from every direction, it actually implodes like this, and after that it explodes. And when it implodes, the nucleus comes very close together, and then they are trying to make fusion there. Yes. So the lasers are very different. It's not the same. Yeah.
Then there is another question. Everything is happening very fast for a very short time.
Yes.
So how does your electronics? Do you have any special electronics that can?
Exactly. The fastest electronic in the world developed is about nanoseconds. So we can't measure above nanosecond.
Something that is shorter than.
So we need something which is shorter than a nanosecond. And what is it? The light we have already is the shorter.
Yeah.
So we take a part of the light and we use the light to measure the same light.
Okay.
So we take a reference light which is as short as the previous the one we want to measure, and we just scan that light over the entire laser pulse to measure the properties of the light.
So this is a smart way to.
This is a smart way,
something that is not really fast enough, but
Yeah.
you employ it to study something that is very fast.
Yeah.
That's
Some very special kind of electronics we have, like a picosecond PD.
Max we can go up to picosecond.
Which are like 200 picoseconds of right
100
side.
picosecond,
Yeah.
200 picosecond right side.
That's all.
And this is perhaps a bit more technical and involved question. Do you make fusion measurements here?
No.
Possibly.
We are
mostly
trying,
not, but we are trying. Sometimes we
trying.
try. Yeah, sometimes we try. So we are trying to produce which is called a DD fusion. So there have been experiments in our lab where we tried to do DD fusion. So fusion with deuteron and deuteron. So we use targets, deuterated targets, and we wanted to fuse it. But yeah, I mean it's in a process, you know. Yeah.
So that's something you are working towards.
Yes, we are working towards.
Hopefully, you will have it
in coming years.
time.
Yes, yes.
It's very difficult to say months or weeks.
Yeah.
Okay, so I just check if there are more questions. Now there is someone wants to know what exactly you are working.
Okay. Individual.
Or even as a team. Your own
so actually in our lab we do everything as a teamwork, because this is a huge lab. You can't do like one person can't do everything. So we like involved in everyone's experiment. Sometimes we do Doppler. Sagar prefers magnetic field, so he wanted to measure magnetic fields and all. And Amya wanted to do magnetic reconnections that are happening. So yeah, there are very technical terms that we don't want to like introduce right now. But yeah, I mean, we are working differently, but when we work, we always work together, because this lab you can't do alone. I mean, yeah.
The question was only to know what you guys are working on.
Yeah.
So there are lots of different things that the team is working on. As you just heard about
magnetic fields,
Doppler shift measurement.
Yeah, and then there is a lot more. So on this note, I think it's time to say thank you to the presenters and thank you to the audience for a wonderful session. And until next time, bye bye.
Okay, bye.